Right. So, so in the first half we talked about what web search engines are. We talked about this information retrieval model. It's important to understand, and how these inverted indices are built. So now we're going to talk about actually how do you know whether the results are good? How do you know if why is one search engine better than the other one? How do we measure that? And we'll also talk a bit about information loss and about ranking. Those are the three things for after the break. Okay, so how do we evaluate it? So first of all, we look back at the model, and so we basically have to match these things, the results, right? So if you want to know if your thing is doing well, you match the results to the information need of the query. Right? So that's not easy. So what you do typically is you match the results to hopefully the information needs. But you don't know exactly the information needs, so you make a guess. But this is important to again remember that the information needs and query are not always the same. Right? So how do you measure? How do you know how well it works? Well, you measure it. So we get into empirical science, empirical methods. So we can just compare two tools, for example, and then count the number of times they were right, and then the one with the most nudges gets a cookie, right? Okay, so but how do we do it? Well, maybe for example you can select a representative set of queries because we want to know not which one is best in finding cat pages, but best in finding just arbitrary information. So we can try to get a set of queries and then use that to fire to these different search engines. And what you typically do is, because what you want to know is not how well things work on queries, but you want to know how well do they match what we actually want to know, right? How well do they match the information needs? And for this, you basically have only one option: is ask people. So this is what makes it a very subjective task. So we need to have human raters that actually judge the outcome or the relevance of search results. So now we get into the part where humans are involved and brings a whole set of interesting challenges. Right, so you can actually check if one is better, and you can actually do statistics on it to see how much better and in what way they are better. Right, so basically, and we're going to look into this in detail, but basically, do they tell the whole truth? Do they tell the whole truth and nothing but the truth? Or do they tell truths but not the whole truth? Or do they tell some other things but the truth? Right, so these are sort of intuitive notions of quality that will give some actual algorithms and metrics for later on. Okay, so like I said, this is important. It's a subjective task, so there's no way in determining whether a web search engine is, let's say, mathematically correct, right? Because we want to know if it gives the right answers, but the right answer might be different for all kinds of people. Right, so let's have so we have an information need. So this is a person. She wants to know something. And then what happens is we get a query. For example, this person enters the query Schiphol and boarding, right? So okay, we know this query, and we might have a guess on what the information needs, but we're not really sure. Okay, so then we feed it to a search engine. For example, I think this is Google, and then we get a bunch of results, and then we can say how good are these results, right? So mathematically, there's no way of determining it, so we just have to ask people. Right, so who says that the first one is probably okay? No one? One? Two? Okay, let's say a majority. Okay, and the second one, is it okay? Yeah, maybe. So the third one, is it okay? And the fourth one, is it okay? No. Ah, okay, so right, I hope that you see already that even this is a more or less clear-cut case, but even here you see some doubt. Whether is the second one really good, is it boarding or is it departures? Is it maybe just slightly different? Would the information be on it? So this is not really easy, but let's say that we ask someone and then we get a judgment, right? So we get yes, 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 no. And now we can say, well, 3 out of the 4 are correct. So this is sort of a measure, right? So this is exactly what we do. But we then normalize these numbers to a number between 0 and 1. Yeah. Before you can answer your question, I have a question for you, which is how do we actually get this error? So why this is wrong, right? But why does it return this one? You can answer.
actually part of my question as well. I think it's because of the stemming where you cut out the end.
Exactly. So this is a real result, and it's a real result of stemming. So you can see basically that Google does stemming. Yeah, very good.
And I guess also the domain name, because most of the time domain name has priority. Yes, and domain name to match people.
Exactly. So they do kinds of ranking why this thing that might otherwise be below is now on top. So this ranking is something we get to later on. But just let's say that it just would be 4 things, then it's still wrong. Okay, so yeah, there was a question still, or no question? Okay, so yeah, you can actually see the stemming here, and it works a lot, but sometimes it doesn't. So that's interesting. Okay, so back to this metric. So 3 out of 4. What does it mean? So typically you measure information retrieval systems on 2 metrics: precision and recall, and these match these notions of the truth and nothing but the truth, and how that works. So precision is, so this is the mathematical formula. It's the number of relevant documents that you have found in retrieved documents, right? So the ones that are right, divided by the number of retrieved documents. So in the previous example, we retrieved 4 documents, and among them there are 3 right ones. So the precision in this case is 3 divided by 4 is 0.75, right? Precision is the notion, how correct am I? How often of the things that I give you am I right? Right. So then the higher the better. And the perfect precision is 1 always, right? So we normalize it once. This is normalization, which means that it's the same if you do it over 1,000 documents or over 10. So recall is another one, right? So this is, do I give nothing but the truth? And this is, do I give the whole truth? This says it's the number of relevant documents that I found, right? So it's the same as this one. But now I normalize it over the number of relevant documents that exist in the corpus or in the world, right? So in this case, I get 3 right answers. But if I know that there are actually 10 documents that match my query, I can say, well, the recall in this case is 3 out of 10, right? So this is the nothing but the truth part. And I always have to be a bit, it's always hard for me to find this one. So if you look at it like this, then a black dot is things that are right. Let's say all the documents about Schiphol boarding. And all the white dots or the empty dots are wrong documents. Right? And let's say that the set of documents that is presented to the user is within a circle. Right? Then the recall is the difference between these things. So how many of the right ones do I find? And the precision is the distribution between these things. So how many of the things that I find are actually right? So I always have to think about it as well. So it's not super intuitive, but think about precision as how right am I, and recall as how many of the things that I should find do I actually find. Yeah.
I understand your definition of recall, but how could you ever know what the total relevant documents on the web are?
So the question is, how do you know the total number of relevant documents on the web? So in web search, recall is very, very difficult to measure. So in other information retrieval systems, usually it's easier. So you can, for a subset of queries, you can actually calculate or just do a manual check on how many pages you should be able to retrieve. On the web, it's not that easy. So on the web, we don't really know. You can do guesses. Right? So you can say, well, I think it's about there are about 1 million pages about cats on the web, and I find 500,000, so now it's half. So this, you're right. On the web, on the open web, recall is very hard to measure, and it might actually be completely irrelevant. So we don't care if I search for Schiphol boarding. Do I really care that I find all 100 million documents, or do I don't care if I find half? Right?
In practical terms, would they do it by just using all the different browsers, the same search term?
For example. Yeah, so you can actually see, okay, well, this one doesn't find that one, so at least we'll just add them all together, and then we have a number. But what you see more in practice is that for web search, you don't really use recall that much, because we know that it's really meaningless. We'll get to that. So that's a very good point. But in general, for information retrieval, recall might be important. So an example with people that I work with on a daily basis is people from the history department, right? So they have a library, and they want to find, for example, in the Second World War, all mentions of a specific person. Right, so if I build them a nice search engine, and I say, well, look, I put all this Google stuff in, and you get the top 10 ranks top, They say, I don't care. I want to know for sure whether I get all the results, because if I'm going to publish a book on this guy, I want to make sure that I have full recall, right? I have nothing, and I don't care if there's one or two wrong ones, I can filter them out. So typically in web search, you care less about recall and more about precision, but in other tasks you care more about recall. And this is a trade-off, right? And this trade-off is actually something you can measure. Right? So this is the system. Often you can build a system and you can tweak it. There's a bunch of parameters you can tune that give you more or less results, right? And so let's say that the parameter is these crosses on the thing. So you can set it very strict, right? So I give you only 2 documents, but I'm really sure that they are right. So typically you get low recall but high precision. But I can also just give you all the documents on the web, right? And then I'm sure I'm right. I know that all my things are there. But so my recall is approaching 1, but my precision is getting really low, right? So typically you have this precision recall trade-off, and you can choose depending on the task that you have to be somewhere on this line. So for the web you want to be here, and for the history example you want to be here. And the more event like this the system works, right? So the more this graph is drawn to that side, the better your system is, because the less compromises you have to do to get more good results. Right? And let's say this graph, so this is measured by having a sort of combination of precision and recall, which tells you how good is my system in general, with respect to both precision and recall. That's called the weighted average mean, harmonic mean, sorry. And that's basically this calculation, right? So it's basically just a sort of fancy average over the precision and recall that makes sure that it always adds up to 1. Right, so, and these 3 measures, so precision, recall, and F measure, are ones that you should be aware of and know. So they're not super complex, but you should know. Yeah.
Do we remember the formulas as well, or is it okay to know the concepts of?
You should be able to calculate precision and recall, and also F measure. Okay. So precision and recall are, I mean, it looks complicated, but it's basically also quite intuitive how you do it. So we're actually going to look at an example here. So let's go back to the Schiphol boarding example. Like I said, there's 3 out of the 4 are correct. So precision, right, is, that's a question here, but we already did it. So this is 3 documents that are relevant out of the total documents. So 3 divided by the total number of documents. So precision is 0.75. Okay, so recall, and now I have to do the trick. So let's say that I know, or I guess that there are 6 relevant documents. So what is recall then? 0.5, yeah, right? So it's just the number of relevant documents, again 3, but now divided by the total number of relevant documents that are out there. So it's 0.5. And the F measure, we don't have to do it out yourself, but that's, right, so it's 2 times the 2 numbers multiplied divided by the 2 numbers added to each other, and that adds up to 0.6. So that's apparently how good this result is in terms of F measure. And you can do that for a lot of different queries, and then you can calculate the sticks. But again, you have to ask people each time whether this is right or not. Okay, so now we get to the point of recall. Does it even make sense on the web, at least, to consider all retrieved documents, right? So do I have to go to all the 1 million results for cat if I Google cat? And so how does the web work? How does Google work? So we can actually just measure it, and we've been doing that. So there's all kinds of eye tracking experiments that have looked at how people look at the first pages of Google, right? So this is let's say an average heat map of how people look at the Google result page. And you can see that people actually look and click on the first 2 links, and then it degrades quite fast. So this is link number 10, 9, 8. So you can see that people don't even look there, let alone click. And so you can actually also analyze the click rate. So this is just measuring on the web. So you can see that on average, 56% of the clicks are on the first hit.
Just on the previous page.
Yeah.
Is this old? Is this why they move sponsored links to the top?
Yeah. This is a bit older. So it lacks the Google Knowledge Graph thing here. But you see that people are still trained to look at the top things.
But is that why they moved? When you have sponsored links now in Google, they have it.
Oh, they are aware of this, so they do that. Yeah, they do it all the time. So they're always in this sort of in this split between giving you the right information, but also making sure that Sergey Brin can drive this super fancy car, right? Yeah. So, I mean, yeah, of course. So they know, but they also know that if they put the first 3 things here are sponsored links, and they're crap 50% of the time, okay, people are going to think about Bing maybe. For the first time, no. Okay, so this is clicks, right? So you see the same thing. So you see that actually, you know, the bottom 4 links make up less than 7% of the clicks. And it's interesting that actually people click more often on the bottom link than on the 4th from the bottom for some reason. So this is like, there's all kinds of psychological things going on here, but it's also about, well, apparently most of the time Google's right, and I don't even have to look. So basically what this tells us is that it doesn't really, you need to be correct in the first few links, and it doesn't really matter what happens down the page, let alone, you know, in these oohs. Right? So how many of you in the last 5 days clicked on the 8th ooh, right? No, not you. Yeah, so if you know, sometimes you have to, but it's really, it's not, you're almost expecting that your answer magically pops up in the first 3 hits, not in the first, you know, if it returns 1,000 links, it's up to you to search the right one. Right, so ranking is super important. And also that's what you can actually, so if you want to measure how good Google is, you don't look at all the 1,000 documents and compare them to the 1,000 documents of Bing. You compare the first N documents, right? Because we know that that's important for actual users. Right, so you can determine precision at N or P at N, which is basically the precision if you cut it off at that point, right? So for example, you can say, well, in a system, let's say Google gives me a lot of answers, then you hope that the first one is right, and you hope that the curve goes like this, right? That the more answers you give, the more wrong answers there might be. And if you get a curve like that, then you're doing ranking well. That means that you're not randomly assigning ranks to things, but the things that you actually know are right are getting higher up in the hierarchy. You can also do the same for recall at N, so that's basically, again, you can do cutoff. You only consider the things that are right up to that, that are given up to that point. Right, so precision at N is an important thing, especially in the web context, but also in context with with larger corpora. Okay. Okay, so ranking. So Google does ranking. So this is a result of Shakespeare. Well, if I look for Shakespeare, I get a bunch of very interesting, possibly interesting links. So how does Google do this, right? So do we know? What kind of guesses can we make?
It's based on the number of clicks that people give to a page.
Number of clicks that people give to page. Yeah, they do some measuring of user activity, and then maybe things that are more clicked. Okay, I'm not sure if they do it, but they probably do. Yeah.
The amount of money the company pays.
Amount of money the company pays. Yeah, very good. You have a business.
I think it has to do with how many links there are to that page on other sites.
Very good. This is what Google got famous for and why it works. So we'll get to that on the last 3 slides. So yeah, you're too late with this great idea, but it's a good one. Yeah.
If the content of the website matches with the name or the title or the keyword.
Yeah, so this is why we would throw away the HTML anyway, right? So some text might be more important than others, and we might want to rank them higher. Yeah, very good.
And also the name of the domain.
Yeah, so exactly, domain name, but all kinds of meta information that might point to why this thing should be ranked higher. Yeah, very good. So these are all, let's say, very specific web things, but we can actually also go back to the content of the page and identify if a page is more relevant to a specific query or less relevant. And basically one thing that just always works is if you do something smart with the amount of times that certain terms appear on pages. Right? So this is term frequency ranking. We'll have a look at that because it's so generic and it doesn't matter if you're on the web or not. But all of the answers here is what Google uses, right? So Google does not use one thing, not even PageRank anymore. It's like 30 or 40 different strategies that all add up to this magic result. But they also do something like this, right? So TF-IDF stands for term frequency times inverted document frequency, and that's a metric to determine to what extent a specific word is indicative of the content of that document, right? So you get a weight, a value for each word for that specific document. So is this document really about Schiphol, or does it just mention it once? So one thing is we just count term frequencies, right? But you can do something a bit smarter. You can use term frequency and multiply it by the inverse document frequency. And what inverse document frequency, the intuition behind it is that words that appear a lot in general, like me and cat and house, you know, if those appear on your documents, apologies, it's not really helpful, right? Because they appear in all documents. But if word Schiphol or Shakespeare appears, those are words that are not that common. So if they appear in my documents, they are much more informative, right? So somehow knowing which words appear a lot in the world helps me by determining whether they are important for this article, for this document. Right? So TF-IDF, there's a number of versions, but what they always do is they have some term frequency, so the term frequency for a specific document, and they multiply it by the frequency of the term in the entire corpus. This is the large T. And one very common one is actually where you have the term frequency, so that's now the frequency of the term in that document, but we normalize it by the total number of words in the document. Right? So this doesn't give any preference over long documents, because if I have a very long document, then the likelihood that the word appears twice is much larger. Right? So this is a normalization trick, so that short and long documents are equally weighted. And then the inverse document frequency is the log, and we'll talk about that, of the total number of times that the document appears in the corpus as a whole, right? So how often does the word me appear, or how often does the word Shakespeare appear? And the less it appears, the more important it is for this specific document, so the higher this value gets. That's the intuition. Right, so this is just a version of it. There's different variants, but we'll talk about why this version is very good because of the log in a second. But we'll first look at an example. So let's say we have 3 documents. One is the sentence, the game of life is a game of everlasting learning. Another document is the unexamined life is not worth living. And the third one is never stop learning. So all groups of 5, I guess. Alright, so I'll just take you through it, and of course the slides are online, so you can do it a bit more slowly, but I'll just show you how this works. Alright, so let's first look at the term frequency. So for example, the word the in the first document appears once, right? So the term frequency is 1. But the word, what do we have? Is there one with 2? Game, yeah, the word game appears twice in this document, so the term frequency is 2, right? So we can make a nice thing here. There's something missing here, sorry. So there's a game appears twice, off appears twice, and all the other words appear once. So this is the unnormalized term frequency. Now we can normalize it by the length of the document, number of words. Right? So the first sentence has 10 words, so all these numbers are divided by 10. These are all divided by 7, by 3, etc. So we get normalized term frequency. So this is the thing that is the TF part. Alright, so 0.1, 0.2, 0.2. So now we have a sort of, we can compare these things. They are now comparable. And we don't have any bias because one document is longer. Now, so the inverse document frequency is something that you have to calculate. So you take all the words and you count the number of times that they appear in a document. So the document frequencies, inverse document frequencies for the words is listed here. You can make a table, and then you basically just look them up and multiply them. So you get a TF times IDF. Right? So this is the TF-IDF value. So TF-IDF value is always between a word and a document. So this is the TF-IDF for the in document 1. So now we can see some things. So maybe the color is not so great, but here, for example, the word learning has for document 1 has a value 0.14, and for document 3 has 4.69. So we can use this to rank it. If I type learning, then this document pops up higher than this document. Right? And basically this is because more words appear there. We can also see that, for example, the word is has a fairly low value, right? Even though it appears once. And also the word everlasting also appears once, but it has a higher value than is. And that's because the word is appears everywhere. Well, it appears on twice. But you can imagine that for more documents, actually the word everlasting is more informative in general. Right? So this is sort of a very simple trick to measure, to take term frequencies into account and to see how often words appear. If you TF-IDF is basically in any circumstance a very good measure to rank documents. So this is what a lot of tools use, and you will definitely encounter it again somewhere down the line in your studies. So remember this. Okay, so I promised I will talk about the log. So why is the log there? Right, because it works without logs, basically does similar things. But the log actually tells us how strict we have to be with penalizing words that appear a lot, right? And the log is determined more or less empirically, right? And we can see how we do that. So let's see how often. For that, we need to know how often do words appear in corpora in general, right? Can we say something about it? Yeah, we can do that. We can download the web or download Wikipedia, add all the words, and then right. So I split all the books or the documents into words. I cut them up in spaces. I do all these pre-processing things. I sort all the words. And I count the words, right? So now I count how often do these words appear. So is a lot, everlasting a bit less, and Shakespeare even less, right? And then I just plot the count. So I make a graph, right? So this is what the graph looks like. It's a bit you can't really read it, but here on top this is the word the. Then there's of, and, in, to. Here's was, and then here's where and which, have, but, etc., etc. And we see this very characteristic curve. So we always get this exponential curve that goes down. This means that there are very few words that appear a lot, but really a lot, like exponentially a lot. And there's a lot of words that appear a little. Right? And this curve is something that has been observed in all kinds of other domains, but especially in language. All languages work like this. So there's apparently a lot of words that we use a lot, and very little. There's a few words that we use a lot, and a lot of words that we use a little. If you know that, then you can say, well, if this thing is exponentially distributed, then we can actually use that in our metric to make sure that we adequately normalize for this occurrence of words. So that's what the log does, basically. Right, so formally it says that the frequency of a word is inversely proportional to the rank in the frequency table. Basically, it's just a repetition of what I've been saying. Yeah.
Does this mean that, like, if you have a key search term, that people then just use the thesaurus, look up abstract, like synonyms or words that are similar to that, and then just throw that in their page as well?
Right. So yeah, yes. So that might mean that if you use a web page full of generic words, then it's less likely to be found than when people use specific words. Of course, there's also the thing that people search more on more frequent words. So there's a trade-off. But you're right. To make your page stand out, it needs to match these TF-IDF things, and needs to match less frequently occurring words. Yeah. So that's one trick you could do as a web designer.
Can you then exploit this system, for example, in your meta keywords? You'll just put random keywords.
That's what people have been doing. That's what they've been doing. And Google has been fighting this, right? So they now rank meta keywords differently. But indeed, that's what people have been doing. Very specific keywords that you know that people are still looking for. So this is all part of the search engine optimization strategy. There's a lot of strategies you can be in. Yeah. So there's. Okay, so this is the Zipf's law. You can actually plot it like this as well. So if you plot it on logarithmic paper, you can actually see that those are straight lines. So this is a Wikipedia one, but you can also do it if you do it for the Dutch National Library content, or if you do it for the Swedish subtitles of TV shows. Right? So this is just how language works. So this is a fundamental information law that we can actually use to make our search engines better. Okay, so this is one information law that you should know, but the other one is sort of it counters this, right? Because you could think, well, the nice thing about Zipf's law is that because of the exponentiality, I don't need to know all the words. I can just stop at some point because will have the majority anyway. And Heaps' law basically counters that. Says, well, okay, let's see. If you split the books into words again, you cut them up into space and punctuation, right? I delete all the punctuation again, but I don't sort the words. But I just count words, and every time I find a new word, I give it a +1. Right? So how long does it take until I don't encounter new words anymore? Because that's what you would expect. Right? And then you see this. So you would hope that it would flatten off quite quickly, and after now the 600,000 documents, you wouldn't find any new words. But that's the problem with how we use language, is that new words keep popping up in new documents. Right? So the dictionary keeps growing, so that means that you can't stop. This long tail, right, where all the very few words, is actually significantly larger than the few words that you have at the beginning. So Zipf's law and Heap's law tell us a lot about how information is distributed, specifically language, which is what is important here, and why we need to keep indexing documents in order to understand all the information on the web. Right? So, and these two are used. Right? So, okay, I think I see this. You know, and the speed with which you encounter new words goes down, but there will still be new words encountered even after a very long time. Okay, so again, good ranking algorithms take these information laws into account and they use them. It's not just sort of trial and error, it's actually knowing how this stuff is built and using that knowledge to improve your algorithms. Okay, so we talked about other ranking tricks. So we talked about PageRank was mentioned, I think. Log analysis is the click analysis, you mentioned this, very good. And there's also localization. So for example, if you search for something like, let's say, storm, right, you will find that actually you get information about the storm here, and not about some specific storm. Why? Because your phone knows where you are, and it will send that information to Google, and it will rank your results differently than it will do for someone who is in Hawaii. Right, so the localization influences ranking. All kinds of personalization as well. So if you've been searching for the storm studievereniging, then you will probably find that among your top 10, right? So it will remember what you've been searching. So there's all kinds of strategies based on what Google thinks people in general want to find, right? So it just guesses. It says, well, usually people want to find the things that they've searched for before, so that's why these tricks work. And the last one is the PageRank, which basically comes down to, well, you probably want to find things that other people think are cool to link at, right? So this is the intuition, and we'll see how the intuition works in this slide, right? So PageRank is what made Google famous. Like I said, up till Google, other search engines were reigning. So Alta Vista was doing this, and basically what people found is that they give the right answers, but their ranking algorithm doesn't work. Right? They don't give the right answer in the top 3 things. And even though they claim that the right answer is there, if you only look on page 3, that's not what we want. So the Google guys came up with a very smart, simple idea of how to rank pages. They said, well, usually what you want is you want pages that are trusted, right? So are well known, that people are happy to link their things. Right? So the intuition behind this is that pages that are linked to by important pages are themselves important. Right? So you can see this here visualized. Right, so this guy is has a high page rank, and therefore all the pages that he links to, right? Say, oh, for example, we'll look at this page. They get high scores as well, right? And these are the 4 guys here in the bottom left who wait until someone important links to them, right? So these are the Wikipedias and the Schiphol.nl ones, because if you make a page about the storm today, you say, well, at Schiphol there was a lot of wind today, and then you link to Schiphol.nl, or you link to Wikipedia/Schiphol, right? So this is again sort of the preferential attachment. I prefer to attach to things that are already very popular in full effect and actually being exploited by PageRank. So what Google does is it calculates PageRank values for each website that they've indexed, and they give this a sort of extra boost. They use it as a boost. So they do matching, but then they say, well, things that have a higher PageRank get on top. And it used to be that actually you could see your own page rank. So you could actually see what the rank was that Google gave you if you were in this yellow blob or a red blob. It was actually in the user interface as well. So you could ask Google, what's my page rank, and they would tell you. Or you could even see in the results why my thing was ranked higher. And they stopped doing that, and they also stopped responding to requests to give you the page rank. But it's still there, and it's now part of the strategies of Google. It used to be their power play, let's say the silver bullet, and now it's just one of the 30, 40 strategies that they use, and it's actually now a minority vote, right? So it's not like the thing.
Just one thing on how that's calculated. So what I'm saying is, if a site's really important and it links to you, that's great. If that really important site is linking to loads of different sites,
yes,
that waters down.
Yes. Yeah, so there's a normalization that happens for the number of links, just as it does in the TF-IDF. So this is always this sort of trade-off.
That's to stop people just linking
Yeah, so that's what happens, right? So the first thing that happens when you build your cool secret cat page is you phone your friend and say, hey, can you link me from your other secret? And that's what you got these link rings link rings. That were so basically you would subscribe to a link ring and then you would promise to link to other people. And the only reason was to sort of make sure that the crawler would find you and that you would actually get higher rankings. And nowadays that's less of a thing because that's one of the things in search engine optimization, but there are other things as well, like the meta tags, but also the localization thing, using the right words on in your page. All these things add up to being able to be found. Right. So for this page rank, you have to know the intuition and how it generally works. Okay. So this is it. I'll summarize what I think are the most important things. So web search is basically just information retrieval, but with the web as corpus, and it's the most well-known form of information retrieval because we've all been using it, right? But you can look at it with information retrieval principles and models, and just think of the web as a very, very large corpus that's particularly hard to harvest. But you can do it with crawling. So what do all these search engines do, and all these information retrieval systems do? They build indices on the corpus, and it's called an inverted index. You build them by using crawling, pre-processing, and then actually indexing them in this smart way. Then what you do is match Boolean queries with this. So this is a very simple lookup operation, combining maybe different parts of the query. Right, and then you come into ranking, which is in web search a very important part of this whole thing. Right, but what's important also is that you can actually see that to know whether this is working. There's all kinds of existing metrics that require the use of judgment. So this is nasty because now we can't do it all in Silico. We have to ask people. We have to go out and talk to people. Right, so again, ranking is key, and good ranking metrics take information loss into account. And that's what I like about this, and why web technology is nice, because we have to know something about the world, about how people work, how information works, how language works, in order to be able to build good information retrieval systems. Right, heap law, etc. And there's all kinds of strategies that are added on top of each other, and if you do it well, you can be a search engine optimization person and make money. So that's it for me. I leave you with the search engine optimization wrap, because that's what I always do. Be safe out there, and I'll see you next week.